Okay, the next problem we're going to look at here is going to be 16.9. 16.9, I really like this problem. You've seen this. We did this in statics, a very similar problem to this. But now we're looking at it in terms of dynamics and moving this time. In statics, we looked at it when it wasn't moving. So here we have a cabinet. It tells us that the mass of that cabinet is 20 kilograms. And it's mounted on casters, so it moves along freely. We don't have any coefficient of static or kinetic friction that we're dealing with. And if we're pushing on this with 100 newtons, okay, we want to determine first what the acceleration of our cabinet is, and then also what is the range of H, meaning how low and how high can we apply that force without tipping it over, okay? So that's going to be the job that we're going to do. Okay, so first things first, we want to make a nice diagram of our cabinet. First, if you would, on the left-hand side with the forces, and then on the right-hand side, we're going to do it with the inertia, terms. So let's make a nice diagram here with the information that we have. So this is going to be problem 16.9. And then you guys tell me, the request was given, I think Lex and Christopher looked at it. So we'll do a setup and I'll kind of check along to see if you want to keep going, or if you want to then finish it up yourself. So we'll get it set up here and we'll check back in. So the givens are, the mass is 20 kilograms. We know that P, that force, is 100 newtons. Okay. And then we need to find acceleration, straight line acceleration of that cabinet. And we also want to find H min and H max, which is really the range, the two ends of the range. Okay. So drawing our cabinet, left-hand side here, we're going to look at forces first. Okay. In the middle here is going to be our center of gravity, which then is going to have the weights coming down. Okay, we'll calculate the weight in just a second. We have force P equal to 100 newtons. Our distance H is from the bottom of the cabinet, or from the floor. I just put the cabinet all the way down to the floor just because I'm not really worried about the casters. We're going to call this corner A, this corner B. And there are reaction forces at each case, okay? So we're just gonna show those in place there. We do know that from the bottom, center of gravity going up is 0.9 meters. Okay, and we know that the width of our cabinet is 0.6 meters. So the geometric center, they don't give us this dimension, but we're going to assume based on the picture, and they're not giving us any information to the contrary, that this then would be half the distance in. So this would be 0.3 meters from one side and or the other. Okay. So this is going to be some of our forces side. It's going to be equal to, we're going to redraw our cabinet. And our center of gravity is right about here. And now we're going to identify the momentum, or the mass times the acceleration, right? So it's going to go here, m times a. And we know again that distance up is going to be 0.9 meters. And this is our point A and B, the corresponding corners. Now let's calculate that weight right away, because that's going to be the force coming down here. So our weight, we know, is mass times gravity. So we were given the mass as 20 kilograms. Remember, mass units are always kilograms. So if we see kilograms, it's a scalar unit. We don't identify that with or represent it with a vector. So it has to be a force. And to convert it over to force, in the case of mass of an object, we multiply it by gravity to get that value. So this is going to be 20 kilograms times 9.81 meters per second squared. A kilogram meter per second squared is going to be a Newton. Okay. So our weight then is going to be 196.2 newtons. Now, the first thing that we're going to do is we are going to look at the acceleration. Okay. And as we look at the direction of the motion here, this is in a horizontal direction, which makes sense. Our force is pushing to the right in this case, and we can see that the acceleration, the movement is also going to the right. So step number one, if you would, for our problem, we're going to sum our forces in the x direction equal to mass times acceleration. Okay. So when we look on the left-hand side here, force is in the x direction. The only force that we're seeing in the x direction is the 100 newtons, right? So the 100 newtons, according to our convention here, would be positive. So we would have 100 on the right-hand side, or I'm sorry, the left-hand side, is going to be equal to mass times acceleration. If we look up at the top, we were given the mass of our crate is 20 kilograms. So this is going to be 20A. So solving for A, divide both sides by 20. A is going to be equal to 5 meters per second squared. Remember to put your units in the final answer. All right. So don't forget, don't just say A is equal to 5. A is equal to 5 meters per second squared. That one's done. Okay. Now let's talk through how we're going to calculate the H min and the H max. Okay. So this height, when we push our crate along, okay, and we push it, one of the conditions is it's going to just start tipping. Okay, it's just going to just start tipping. So impending tipping, if you would, in a clockwise direction. And if we imagine what's going on here, it's like we're putting all of the force on point B, and we're just slightly lifting this off A. So what that means is when A is equal to 0, okay, when A is equal to 0, so again, all of the forces on here, that means that it's going to start tipping. So we want to find H when we sum around B, okay, when we sum around B. So A is going to be 0, so that means that this is going to be 0. So we're going to sum around B, all right, on the left-hand side. And our only, we're going to set it equal to the M times A. And then it's going to have that distance there. Okay. So let's set that equation. Sum of the moments around B is going to be equal to, since we're summing moments, we have alpha, or I times alpha, plus mass acceleration. And then don't forget, because it's a moment, we need that perpendicular distance. Okay. So on the left-hand side, we're summing our moments based on summing around point B. A is 0. And then H is going to be an unknown. Okay. But it's the distance to here. And then don't forget to put your weight coming down and the distance from B. All right. And then set that equal to over here. You're summing around B again. So you have to look, what is the distance from B? Don't forget to put this 0.9 in as this rotates that way. And you have to give it a sign. And remember, our convention is in play. So anything that rotates clockwise is negative. Anything that rotates counterclockwise is positive. So the left-hand side is going to be sum the moments around B. The right-hand side is also sum the moments, if you would, around B. This is 0 because we aren't rotating. We are translating. So it's only this part right here. We know what A is. We know the mass. And we know the perpendicular distance. It's right there, perpendicular distance from B. All right. Then the other condition. So you're going to be solving then for H max in this case is going to be equal to whatever your number comes out to be. All right. And I have the final answer given. Then what you're going to do is you're going to do it again. And this time the other condition is when we push on this, where all of the weight is at A and B is going to be 0. Okay. So the third way is going to be when B is equal to 0, you're going to sum your moments around A. So now you're going to be on this side over on the forces. Okay. And on this side over here. Still, we're not rotating. So that's going to go to 0. You're going to have your M, you know that your mass is, you know what your acceleration is, and it's the same perpendicular distance, but make sure that you're still going in, you know, the same direction. So you have to have a negative or a positive there based on the rotation that's being created here about point A here as well. Okay. And then this is going to be your H minimum. Okay. And that'll be the second part of that problem. Is that enough? Do you feel that's enough to keep going and finish it up?
Yeah, I think so. I think I was just getting confused on the weight. Like
Oh, okay.
I was factoring weight as a force into the equation, but it's not, right? When you
No,
sum the momentum.
it would be when you do your moment, right? When you do your moment, it is going to be included and it's going to be half the distance over. So on the moment side for both A and B, you will be putting the weight in. Over on the right-hand side, though, you don't put it in.
Okay.
Or in the math.
Okay.
Yeah.
Yeah.
Mhm.
Okay, I think I have enough. I can figure it
Okay.
out from here.
All right. Anybody else? How do you feel about that?
So we just do the moments around those points and we should get the heights.
Yep. Those will be your only unknowns.
Okay.
All right. Then I am going to stop the recording here.